So good afternoon, and thank you for the opportunity to speak in this abstract session. I apologize that I can't be there in person, but I'm excited to tell you a little bit more about platelet transfusions and the role of B-cell and T-cell epitopes in the state of refractoriness. So transfusions are a common treatment for platelet depletion, which is a scenario that you might encounter if a patient is undergoing chemotherapy or in preparation for a stem cell transplantation. But there is a complication. If you get repeated transfusions, it can lead to a state of refractoriness, which means that subsequent transfusions do not make an effective increase in the number of platelet counts. So it's kind of a platelet rejection situation. There's many causes for this. It's often caused by non-immune or immune causes, and specifically it can be caused by the development of anti-HLA antibodies, especially HLA-A and HLA-B. So how do these antibodies develop? Antibodies develop through a process of linked recognition. In this figure, we have a donor platelet in the center. You can see that this donor platelet is expressing class 1 HLA, and class 1 HLA has a lot of these B-cell eplets on the surface. These B-cell eplets can be recognized by the patient's B-cell receptors. What can also happen is that the HLA gets endocytosed by an antigen-presenting cell. So the HLA gets broken down and presented on the patient's own class 2 molecules. So this up here is a T-cell epitope where the donor HLA is presented on the patient's HLA and recognized by the patient's immune cells. So you would need both the B-cell and the T-cell recognition to provide the T-cell help and make the antibodies against the donor material. Luckily, we have some tools that can predict this. We have the HLA eplet registry, which lists a lot of these B-cell eplets. We can use this to calculate B-cell epitope mismatches. We also have this perch tool. This perch tool calculates the number of indirectly presented T-cell epitopes. So we can use these two computational tools to look at linked recognition. We came up with a computational pipeline. The first step in this is to do some population simulations. We looked at some NMDP haplotype frequencies and paired them together in a process of random mating to create these ethnicity-specific populations. These populations are defined by the members' HLA types and also the expected frequency for how often we would expect them to show up. From these populations, we selected a few candidate patients, and for each of these patients, we assigned transfusions from the population. These are randomly selected, but they're weighted by the expected genotype frequency within the population. From there, we do some epitope prediction using these eplet and perch models. The results from that look like down here, where we have the eplets per transfusion. Each patient and each transfusion, we can see how many eplet mismatches are predicted. And this second figure here is the cumulative T-cell epitope. So after subsequent transfusions, we can see how many cumulative total epitopes the patient has been exposed to. How does this look in a chart then? These figures are showing a cumulative epitope mismatch. So the x-axis is the number of subsequent transfusions, and the y-axis is the number of epitope mismatches that they've been exposed to. So we have the eplets, B-cell epitopes on the top left, the T-cell epitopes in the bottom left, and a combined and weighted figure is the bigger one on the right. So we can see that these individual patients do have distinct profiles. In some of these patients, they're quickly nearing their maximum epitope exposure after only a couple of transfusions. And some of these other patients are a little bit more slow on the uptake. They're having smaller epitope mismatches, and ultimately these patients will reach different peaks here. Some of these patients will, after a few transfusions, have a high level of total epitope mismatches. We can also see that in some of these heat maps. In each of these heat maps, each heat map represents a different patient. The y-axis is the eplet mismatch, and the x-axis is the T-cell epitope mismatch. So we have 3 European Caucasian patients, and 3 Asian Pacific Islander patients, and 3 African patients here. Up here in the top left, we can see this European Caucasian in a European donor pool is kind of a best case scenario. Each one of these little dots represents one of the potential donors, and we can see that for all of these, it's skewing towards the lower left of the plot, meaning that all the donors will have a lower epitope mismatch. And of course, if we look at some of these other patients, we can see that they start to skew either towards the top or towards the right, meaning that they have either higher B-cell epitope or T-cell epitope mismatches. So the conclusions from this: transfusions do lead to a cumulative epitope load, and this varies widely by patient. So some patients are higher risk and lower risk than others. And what that means, and what we already know, is that there's imbalances in compatible platelet availability. If you are a European in the European population, you probably are going to have better luck than someone with a different ethnic background in this population. So they're already doing HLA-A and B allele matching for platelet transfusions in many cases, but I think this could be improved using some prioritization and some improvements. I think we can come up with epitope-focused models that define not just allele-level mismatches, but focusing on the eplet and T-cell epitope mismatches to come up with a better strategy. This would ultimately prioritize the high-risk patients and maximize the number of cells that are available and hopefully minimize the complications. So I've been working on this with Eric Spearings. It was a lot of the initial work was done by Joanna, a patient in our group, and I've been working with Sean, Kirsten, and Emma, and we have a nice collaboration with Ellen at San Quinn. So thank you.